Physicists, I do want to wish you a very happy National Dance Like a Chicken Day. It's one of those national holidays that I did not realize existed until 11:30 last night. And I was like, well, I guess we need to celebrate it then, don't we? So anyway, happy National Dance Like a Chicken Day. Also, happy last quiz of the year eve. Tomorrow will be the last quiz that we take in physics, which is pretty exciting. What's that?
Oh, but then we have the final.
So we do a final quiz. But I'm just saying, like, we got to celebrate when we can.
All right.
Yeah. So we'll also celebrate when the final comes. But for now, we just want to remind ourselves that we have a quiz tomorrow over circuits. Okay? So we've spent a couple of days working on things. We did the light bulb lab. That was the one where we learned what series and parallel were. Okay? And we also did the Ohm's Law lab, which we started on Friday, finished yesterday, getting our data. And then you were to graph some things. Today we're going to talk about kind of how that all fits together, work on a few problems, maybe do a couple ranking tasks, and then that'll probably fill up our day. Okay? So at this point right now, what I would like you to do is to get your notes out. I don't have any handy dandy sheets for you today because you can just write this stuff down. We've got this. Just a couple of reminders. This is the list of homework. I did pull out the answers, so I've got those. I have not put them up on Canvas yet, but I will probably during 7th. If you like to take pictures of my board, this would be an appropriate time to do so. But this is all the homework that you should do before you come to class tomorrow. Okay? At this point, you don't have a lot of time to do a retake on the quiz we have yet to take. So best to do this homework now so that you do well on the quiz tomorrow so that you're good to go. Does that make sense? All right. So there you go. Well, and like I said, if we have time, I'll just throw that up there so we can finish working on problems later. But right now we're going to take a few notes about circuits and how they all work. So yesterday, we're just going to kind of bounce back to our life yesterday. Yesterday we finished a lab that I called, without maybe even mentioning it to you, and this was a nice lab because it was not only an opportunity for you to show me that you know how to do labs, right? Because you're going to turn this into me by Thursday, right? With your graph and your analysis. It was also an opportunity for us to establish some physics principles. So to kind of put that all together, can you remind me what the two things that we measured with the multimeter, what were those two things that we measured? Do you remember what was one of them, Ben?
Voltage.
We measured voltage. And we've defined it a few times, but I want to make sure that you understand what it is. What is voltage? We've kind of talked about it in some different terms.
It's got something to do with the electric field of the terminal.
So it comes from what? Let me, and then I'll come right back to that. Is that okay? What in a circuit gives you a voltage or a potential difference? Do you remember what part of the circuit provides that voltage?
The resistor.
Good guess. It's not the resistor.
Oh, the battery.
It's the battery. Yes. So the voltage is provided by the battery. Okay. We said this, I think, before, but voltage can also be called potential difference because you're measuring from one point to another, and we're really, the battery is really giving electrons potential energy. It's not gravitational potential energy, though. What kind of potential energy are we giving them? Don't overthink it. Talking about electrons. Yeah, it's electric potential energy. Okay. So the voltage is provided by the battery. It gives the electrons electric potential energy. And the other way that we kind of know that, or we talk about that, is, Isaac, what you said, which was that when a battery is wired in a circuit, maybe we should say in a complete circuit. Okay. It establishes an electric field in the wire. Okay. There's not going to be a quiz question on this tomorrow, but just so that you kind of have a sense, if you take a little slice of the wire that you were dealing with yesterday and you look at the electric field and we draw a picture of the electric field, remember we drew electric field lines for charges during the last quiz, the electric field would look like this. It's just straight lines and it's telling those charges where to go. Okay? That's what the electric field looks like when you have a battery put in a circuit. So that's one of the things that we measured. But there were two things that we measured with that multimeter. What was the other one? The current. Yeah. What is current? What is it physically? What does it mean? It's a flow of charge. It is. We did. We measured it in amps. Okay. And so it's like counting the number of electrons or the amount of charge that's flowing through any place. Okay. In a given amount of time. It's charge per time. Okay. Life is good. I've repeated this conversation with you a few times. We talked about it on Friday. We talked about it on Monday. We're talking about it today. Any chance you might see it tomorrow on a quiz? I haven't written the quiz yet, but I would imagine those are things that we'd see. Yeah.
Well, when we did the lab and we measured the current, we got milliamps in the thing.
Yes.
We're writing measured current on our table. Do we need to convert it and move it over to regular amps?
You will. Yes. You will need to include, yes, you will need to measure it in amps. So you're just going to move it over 3.
And what's it mean if we get a negative?
So basically what that means, here, let me just draw a picture for you to maybe help this make sense. So if this is your circuit, right, and the current, and I'm not going to get bent out of shape about what direction the current is going, but the game is that if you put, because you had the red and black leads, right? So there was one here and there was one here that go to our multimeter. So that is measuring the electrons that are going like this, right? If I flipped the red and black leads, then the current would be going backwards through the meter.
We did that a few times.
That's all it is. And so the negatives and positives for both current and for voltage don't matter. It doesn't matter if you have negatives or positives. So this is measuring voltage. You may want to write this down again just so you don't forget to. And if I wanted, that's not measuring voltage, that's measuring current. Please excuse me forever. Okay, that's measuring current. That's an ammeter. Measuring voltage is going to be across here. Oh, I'll bring that over. That's a voltmeter. A voltmeter is measured across. So again, if you switch the red and black leads, then you would get a negative or positive value. But the negatives and positives don't matter for our purposes.
So should we just put up a magnitude?
Magnitude is fine. In fact, while you guys were finishing your lab, I went back and I made some changes. And one of the things that I changed was write down the magnitude. Yes. Yeah. Yeah. Okay. So those are the things we measured. And then I asked you to graph your data. And you may have done that already. I know some people did that in class because they had a little time. Some people did not. But spoiler alert, for those of you that did graph your data, can somebody help me out? What does the graph, well, first of all, y'all can look at your lab unless you turned it into me. What were you putting on the X and Y axes? Take a look. It's in the data analysis part. It's at the very bottom of that lab. What were you supposed to put on your X and Y axes? What's that? I don't remember. What? I do, but yeah. Y is voltage, and X is current, right? So if you have not yet done this, write this down in your notes so you don't forget. Remember, by Thursday, I need this, right? So voltage is measured in volts, and current is measured in amps. And to be clear, because that's the question that Isaac just asked, but again, just to be clear, many of you, when you got your measurements, measured things in milliamps. Remember, milli means times 10 to the negative third amps, which means that you'll need to move that decimal place to the left 3 times. Okay? So just for example, so if you had 3.7 milliamps, that was what you measured. Everybody with me, just to make sure we're not making any silly mistakes here, how many amps is that going to be? So we're going to move it to the left. How many times? 3 times. 1, 2, 3. So it's going to be 0.0037 amps. Okay? So I just want to make sure that you know that, because when you graph it, you want to make sure that you're graphing the amps, not milliamps. Okay? Otherwise, things aren't going to work. Now, here's really where the spoiler alert comes in. For those of you that have graphed it, what does it look like? It's pretty like a straight line. Have you noticed that most of the things we graph in this class are straight lines? Maybe because I really like straight lines, right? And because we can learn stuff from straight lines. So you got something that's pretty much like a straight line. Again, you might have some off, but you're gonna be able to draw yourself a best fit line. And then, what do you think you're gonna do with it? You're going to find the slope of it, right? So you're going to find 2 points. I'm giving you all the tricks here, right? So you got your dots. You're not going to use your dots to find the slope. Say, no, Miss Kay, I would never do that, right? And then you're going to find the slope between 2 points that are on the line. And that slope represents something pretty cool. Anybody know? And or take a look at your lab. It is. It's the value of the resistance. Yes. The slope is the resistance of your resistor. Okay? So this is where the physics takes place, right? The experimental physics is what you just did and what we're doing with our analysis. And now the theoretical physics kicks in. You've got a line, y equals mx plus b. We're playing the backwards game, friends. We usually do it the other way, but today we're going to do it this way. Here we go. So y equals mx plus b. That's my equation of a line. Every time, always. What's my y value? What's on my y-axis?
Sorry, voltage.
That's okay. It's voltage, right? It's voltage. What's my x value? Current. In general, my y-intercept should be really, really close to 0. So we're going to get rid of that b. We don't want it. We don't need it. Catch you later. And then our slope is the resistance. Okay? This right here, the thing that you have discovered by doing this lab, and I don't want you to sell yourself short. You have legitimately discovered, or you will soon, if you haven't done the graphing yet, you have discovered this relationship. Did somebody else know it before you? Yeah, but you found it. You figured it out. Usually when we write it, the way you generally will see it, like, I don't know, maybe on an equation sheet. This is the last equation on your equation sheet. Right here it is. V equals, we usually write it IR. I don't know why. Maybe they just like it in alphabetical order. I don't know, but that's the way that we generally write it. Okay? And this right here, this equation is known as Ohm's law. We've just done every single equation on that equation sheet. That's amazing. When I gave that equation sheet to you in remember seeing your faces. You're like, oh my God. Right? And now you've done them all. Like, that's it. It's here. It's there. It's so exciting. I do want to make sure you understand it and know what it means, though.
Are you going to give us the accepted values so we can pick it up with the errors?
You have them because you found it on the front.
Oh, yeah.
Yeah, right? Does that make sense?
Yeah.
Yeah. So you have the accepted value. That's the thing that you read from the lines. Yeah. So you know your R, you know your I, you know your, so you can, everything's good. Yeah. Now, I do want to just make sure things make sense a little bit here. And from a theoretical physics perspective, I want to make sure that you understand the cause and effect of a circuit. I kind of alluded to it before when we were doing our definitions of voltage and current, okay? I don't know if you remember. It's been a really long time ago. I'm just going to put a little like reminder bubble over here. A long, long time ago, we wrote down an equation that looked like this. Do you remember that?
Yeah.
We wrote it down this way. Even though most people write it F net equals MA. But I insisted, at least for a little bit, that we think about it this way. And the reason for that was because an object accelerates as a result of a net force acting on a mass. Do you remember we said that? An object accelerates as a result of a net force acting on a mass. So this is the cause and this is the effect. Okay? We're going back to like, I don't know if you guys did in kindergarten, but I have very distinct memories of like having to put cards in order. Like you have this one and this one. Which one's the cause? Which one's the effect? Right? Like a kid running up and about to kick a ball and then a ball like bouncing away. Ball bouncing away before the kid kicks it. Okay? That kind of thing. Cause and effect. So this right here, the F net over M is the cause. And the acceleration is the effect. Okay. There's a very similar experience when it comes to Ohm's law. On your equation sheet, it's written V equals IR. Most people, if you ask them, they're going to say V equals IR. But from a physics perspective, it should really be written as I equals V over R. A current, okay, or charge moving through a circuit is the effect that is caused by a voltage, energy from a battery, given to electrons, traveling through a resistor. Okay. Let me give you another little example to help with this. If I have a circuit that looks like this, you know what? Well, we'll leave it like this. Am I going to have any current? It's wires and a resistor.
No.
No.
There's no battery.
There's no battery.
So there's no energy.
Okay? There's no battery. There's no energy. There's no voltage. Okay? So we would say no voltage, no current. Okay. I'm going to go back to our little example that we had before just to kind of continue that thought process, right? No net force. What's the acceleration going to be, friends? 0. Same thing. Does that make sense? No net force, no acceleration, no voltage, no current. Okay? Now, let's go ahead and put a battery in there. And a resistor. I want you to compare this one versus, we're taking a couple of little brain steps here, but I think it'll be good. Let's say these are both 6-volt batteries, just for kicks. And all these resistors have the same 1 ohm resistance. I'm just putting numbers in. I'm not going to actually do any math. I just want you to kind of have some numbers here. Now we have voltage, right? Once we have voltage, we have current. We haven't really talked about this, but let me kind of push you this way for just a second. If I have 1 resistor, and I compare that to a circuit that has 2 resistors, which one do you think has a higher resistance? Any guess? More resistors means more resistance. Does that make sense? Now, I would be a very, very bad physics teacher if I didn't put a little asterisk there, okay? Because that's only true if I have them in line with one another, okay? So I'm going to write down, I'm going to say more resistors in, what kind of a circuit is this? When they go in line together in a loop? Series? Yeah.
So if the diagram on the left, if that had 3 ohms, would the one on the right still have more resistance, or would the one more resistance be on the left?
If this one had 3 ohms, is that what you're saying?
Yeah.
And this one only had 2, this one would have more resistance. Yes. If we had another week, we would do all of this and it would be so fun. But stupid snow days, right? Shaking our fist at January. Don't have time for that. So you have to do that another day, okay? But as I should say, more resistors that are the same, more identical resistors. Thank you for clarifying that. I really appreciate that. I'm trying to kind of gloss things over, and I know that I'm missing a bunch, so I appreciate you saying that. More identical resistors in series, that means more resistance. Is that okay? Now, other questions about this before I take the next step? If I have more resistance, what's that going to do to the current? Just think about physically what it is. I've got charges that are moving through a circuit. Are they going to be able to move as fast if they have more resistance? That's going to slow them down, right? Yeah. So more identical resistors in series, more resistance. The greater the resistance, the lower the current. If I have no voltage, I have no current. As I increase the amount of voltage, what do you think that's going to do to the current? Increase the voltage, that means I'm lifting them up higher. They've got more energy to lose. What do you think that's going to do to the current? Take a look at what the equation says too. The bigger the voltage, what's going to happen to the current? It's going to go up. How are we doing, team? We okay? So cause and effect, cause and effect. This is the cause. Okay. Hold on, let me just say this one more time. So voltage or energy given to an electron traveling through a resistor, that is going to cause a circuit. It's going to cause a current to move through that circuit, charge to move through the circuit. Okay, go ahead.
So what was your original question with the one figure on the bottom?
I don't remember. Just comparing this one versus this one, which one has more resistance?
Oh.
And as a result, which one's going to have more current? Does that make sense? Okay. How are we doing, team? Are we doing okay? Is this making sense? Okay. So the reason that I wanted to spend some time with this is that I don't want you to just use that equation, plug numbers in. Like, that's part of it. Will there be a question like that on the quiz tomorrow? For sure. Okay. But I also want you to understand this. I want you to understand the theory behind it. Like, why is this equation true? It's a cause and effect situation, cause and effect scenario, just like the MA stuff. Okay. Can we try a couple of ranking tasks, and then we'll do a couple of practice problems? I feel like that's a better order than I had originally had in my head. We haven't done ranking tasks for a long time. And I'll be honest, you guys, this is probably the last day of ranking tasks. I know that I can hand you the Kleenexes if you need them. Okay? Josie's like, thank goodness. I can even send them to you if you want, Josie. Like, if you want something to do over the summer, I got a whole book of them. So if you want more, just let me know. But right now we're going to go ahead and look at this one. Identical batteries are connected in different arrangements. So this kind of goes to the stuff that we were doing yesterday when you were connecting batteries in different orders and different situations. I'm going to give you just a minute to take a look. I'm going to get some boards out so you can discuss it and then put them on boards. Does that sound okay? Yeah. So let's see some boards. What'd you say? CEBDA, CEBDA. Do you guys have a board out?
No.
Do you not have anything, no ideas at all? Give me something. Give me something. I've got a few different answers here.
What did they say over there?
I don't know. I'm going to write it down right now. C equals E greater than B equals D greater than A. You said E greater than D greater than C greater than B greater than A. Is that the same?
No, they have C and D.
Oh. Do you want to put up something or no? That means you have to figure out what's right because you got 3 answers.
Yeah, let's go.
So let's see. Identical batteries connected in different arrangements. We want to know which one's going to have the brightest bulb. So how do we know? How are we going to do this? Any ideas?
I just thought about when we did the parallel
Mm-hmm.
bulbs. The bulbs are a lot brighter than when we do series.
Okay, so that's true. When you're talking about light bulbs, that totally makes sense. So you're saying when you had this one versus when you had like this, is that what you're saying?
When they were,
Oh, and then you want it in parallel like this?
Yeah.
So this one was brighter? That's kind of where your thought process was? Okay. So you're saying that because these are in parallel, then they're going to be brighter, or this one's going to be brighter. That's where your thought process was? Okay. Other thoughts?
Definitely think B is greater than. I think C is greater than B and greater than A.
C, you think that these 3,
Because C, B, A.
you think this one's bigger and then this one's bigger, at least those 3?
Yeah.
That's where you're at. C, B. So that kind of matches with what
Yeah. I'm just not sure.
they said. Okay. What do you guys think?
I know A is like the lowest. That's for sure. A is
The lowest. Okay, so we know that for sure. We're going to lock that in. A is the lowest. Okay. What now? We know that E is the biggest?
I don't know.
yeah. No,
We had them equal.
You had E and C equal?
Yeah.
Why?
3 batteries.
Seemed to make sense.
It's brighter if it's brighter.
You're just trying not to lay out the
Okay.
I don't think that like the way you position the batteries affects which changes the brightness.
Okay.
Or that it's just like
So that's why you're saying that, like you said, C and E are the same, right?
Yeah.
D and B are the same? Okay.
They'd be the same amount of voltage.
Okay. So, okay. Emma's got her face looks a little.
Wondering just because when you were messing with like our series stuff, depending on which like wire you connected it to, it may pull brighter or lower. And then E, I just know that make a difference that all of the negatives are connected instead of the negative to the positive like in C. But C is negative to positive, so it have brighter. Charge would be brighter anyway.
Literally and figuratively. Yeah.
So you wouldn't get
Yes.
any brightness from those ones.
So the game is, and we did this is what you did yesterday in your lab when you had 1 bulb, 2 bulbs, 3 bulbs. You hooked them up like this, like A, B, and C in series, right?
Yeah.
So there were a couple of people, I can't remember who was in here, the other class, where like you had the positive going to a positive and then you weren't getting data that made sense. You have to go positive and negative. So basically what this is doing, if generally most batteries are like 1.5 volts. And so that means that it's lifting up those electrons and giving them a little bit of energy. Does that make sense? So we're lifting it up. If it's this one, I'm going to lift it up from here to here, right? If I've got 2 batteries in series, that means I'm lifting it up from here to here and then here to here, okay? So I'm giving it more energy, okay? More energy means it's going to be a brighter bulb. In this one, I'm going to lift it up 1, 2, 3 times, okay? This one, each electron is only going to go either from here or from here. Does that make sense? So these are like even. So that would be like lifting it up and then just moving it over and then dropping it down. Yeah.
What if they were switched?
What do you mean? Tell me what you mean by that.
It's D and E, like the batteries.
Flip like
Like, what
If they were turned?
Yeah.
So, okay, I just want to make sure that I'm understanding your question. So I think what you're asking is, if my stylus would work, if this was the negative and this was the positive terminal, is that what you're saying? So in that case, then this would be negative to positive and negative to positive. So that would be exactly like this. Do you see that difference? Yes. So Leanne said, if I flip these, how will that affect it? And then it would be just like B. So then your thought process would be okay.
so they are
Right.
the same. It's like
Well, hold on just a second. Yeah. I mean, this one and this one, yes, it would be, hold on. Let me make sure I'm saying that correctly. This is going negative to positive out. This is going negative to positive to out. Mm-hmm. Yeah. I don't speak Espanol, but tell me your question in.
So it doesn't matter if they're lined up versus like this way versus this way?
So if it's like this, then it does matter.
Okay.
This would be like one battery runs out and then another battery runs out. So this one would last longer than this one. By that I mean E would last longer than A, but they would have the same brightness
Okay.
because you're still just lifting it up 1.5 volts each time. Okay?
the bulb still lights up.
So the bulb would still light up. So tell me what, based on our new knowledge, what's the answer? C is greater than B.
Yeah.
D.
Oh, I should have said B than D. Yeah, I was trying to be alphabetical and then I kind of failed. Is that making
E is
sense?
the last one.
Oh, is there an E? Oh,
E is
gosh,
the
thank
last
you.
one.
Oh, so I was being a good kid. I just wrote the wrong letter. Excellent. There you go. Thank you.
Explain like what you mean when it's going like it's just going up and then it's just going back down and up and back down on the.
So it's like you're not doing more work. You're not giving it more energy. It's just like moving over. It's got the same amount of energy the whole time.
Okay.
So
Yeah.
wait, D and E would light up?
D and E would light up just as much as A.
Oh.
Yeah.
So it's not a parallel?
So the thought process that you were going through was not bad. It was just that when we were doing that on whatever Thursday, that was for light bulbs. So that was like getting rid of energy. And this is for batteries. So it's a different rule. So what you remembered over here with the parallel versus series, the parallel will absolutely be brighter than the series. It's just that when you're talking about batteries, it's doing something different. Does that make sense? Yeah. Thank you for clarifying.
So if we were applying this to real life, why would someone want to have 3 batteries connected if it's going to have the same brightness all the time? Is it just going to last longer?
You wouldn't, but it would just be, you would just have more longevity. Backup power, right? You don't want to necessarily have, that's why you have multiple, like if you have a backup power source,
Gotcha.
you don't want to like make the toaster or the whatever, like work really, really well. You just want it to work consistently more and more time. Yeah. More? Can we do some more? Let's do one more, I think. Hold on, let me look at this one quick. Yeah, let's do this one, and then we're going to look at a couple of practice problems for Ohm's Law. 2 light bulbs and a switch are connected to a battery as shown. So we're not freaking out by the switch, right? It closes or opens just like we can turn the lights on and off. When the switch is closed, will the brightness of bulb B increase, decrease, or stay the same? And then in part B, I'm less concerned about, but I want you to know part A. I'm going to give you a couple minutes to talk about this with your table mate or table mates.
Well, no, I want to be
You would like to discuss the answers, what you're saying? Oh, okay, well, let's talk about it. Part A, when the switch is closed, the brightness of the bulb will increase, decrease, or stay the same. What did you say? Write it down. 1, 2, or 3.
Oh, we did.
Remain the same, remain the same, remain the same, remain the same. Decrease. Okay. Why? Explain. Explain your reasoning.
The switch isn't even in the thing. It's just like a wire off to the side. It's in nowhere land.
So let me ask a question here real quick. If the switch is open, are either of the light bulbs lit up? They're both lit up. How does the brightness compare, assuming they're the same light bulb, same kind of light bulb? They're the same. You did this, right? Yeah. Now, why are they the same? They're the same because electrons are going around in a circle, aren't they? It's just a little series circuit. Whee! Oh, you're on free, so you can't see my pretty green line. There you go. We close this switch. Now, how many different choices do electrons have?
I think some of them are going to go here.
So now some of the electrons are going to go, oops, come on, silly thing, are going to go like this. Yeah?